Kind of a classic incline plane question. This one though, we're pushing it to get it to accelerate up the hill. So read it over. We've got a 50 kilogram mass. It's a 10-degree incline. There's some friction to contend with, and it's accelerating up the hill. I'm always going to start with a free body diagram. For this one, we've got our 10-degree incline. Our object is on the incline. It's got a mass of 50. Three main forces acting on it. Sorry, four forces acting on it. Gravity, always straight down. We'll deal more with gravity in a second. We're pushing it up the hill. I didn't put enough words in the question, but since it doesn't say different, we're going to assume that the applied force is parallel to the hill. Normal force, the surface reacting. And then the one that I almost forgot, we've got friction downhill. So free body diagram would look like that. When I tackle these, I'm always going to consider the components. I label them as perpendicular and parallel to. So there's a part of gravity that's perpendicular to the incline. If we start with that, since the question doesn't say anything about this object trampolining into the air or falling through the surface, I know that the normal force is balancing out that perpendicular component of gravity. The 10-degree incline means there's a 10 degrees in our triangle in there. When we eventually turn this into a right angle triangle, the perpendicular component that I need to know about is is adjacent to the angle. So that means it's a cosine relationship. So the normal force, which we'll need eventually, is mg cosine of the angle. If we flip to the parallel component, we've got a parallel component of gravity. We've got a tug of war going on. And the parallel component, if I set up F net equals ma, there's only one force pushing it up the hill. That's the applied force. Eventually, that's what we're going to be figuring out. We've got to push it hard enough to overcome gravity, the parallel component, and we have to overcome friction. That's going to be equal to m times a. For this one, we don't know the F applied. We'll work on that. Well, we know Fg parallel. We'll get that in a second. The friction force is always mu times Fn. So F applied. Fg parallel is opposite the angle, so that turns into a sine relationship, mg sine the angle. The friction force is mu times the normal, and the normal is mg cosine of the angle, and that's equal to ma. This is almost a standard for if you're pushing something uphill against friction. In this particular question, we don't know F applied. So I'm going to flip-flop things around and we'll solve for F applied. For the numbers I made up for this one, F applied is the MA. In this case, the M was 50, the A was 1. It's going to change to addition when we bring it to the other side, so we're going to add on the parallel component of gravity. So that's the 59.8 sine of the angle. And we're going to add on the friction. The coefficient I made up was 0.25. 59.8 cosine of the angle. You can double check, but when we get out our calculator and crunch that out, within rounding, dealing with those cosines, I'm getting roughly 256 newtons.